I'm Dr. Jensen, and I'm currently at the ITESM Toluca campus in Toluca, Mexico. The lecture today is going to focus on modeling repair and reparameterization. The discussion is really going to try and focus on how do we get a topology optimization result brought into our CAD system, and bring it in, what do we actually do with it? So we have for the last week been working on a control arm as the lab exercise, and each of you should be getting close to having a result similar to the image that is in the upper right-hand corner. Yours may look slightly different from that, but it's a result that is going to come out of what is called the OS smooth portion of HyperMesh. And in the lower right-hand picture, what we have is a little diagram that was taken straight out of the OptiStruct help information. And what you can see from that diagram is that on the left-hand side, it says that the topology result, whether it's topography or shape, we're dealing with topology. The topology result is going to produce what are called isosurfaces. Those isosurfaces can then go through a smoothing algorithm, and the result of the smoothing algorithm can either be a Laplacian smoothing or it can be an optimization-based smoothing. And once you have that smoothing result, then that information is dropped down to a phase of either doing a reduction, a remesh, or a tetrameshing result. The tetrameshing is a very new feature that's been added to the OptiStruct. And so you'll either do a reduction or a remesh, and that reduction and remesh is what eventually is then sent as an output file. And the output file can either be a finite element mesh, and so you can take that finite element mesh and take it off to a traditional finite element program like ANSYS or Nastran, and you can then resolve that resulting mesh directly in a finite element solver, which is not what we're going to be doing. We want to either grab the IGES file or the stereolithography file, the STL. So we can either output the result that comes out the bottom of that diagram. We can output it as either an IGES or a stereolithography. HyperMesh also allows you to put out a Hyper 3D file, and that's for the Hyper view. It's for a visualization of your result that you can look at. So really the focus of today's discussion is going to be taking the IGES file or the stereo file and taking that into the CAD system. So the topology model we want to bring into NX or CATIA. I apologize to the CATIA student. I tried last night and this morning to get linked back to BYU so that I could get a CATIA license and prepare this lecture for both NX and CATIA. For some reason, I could get the NX license and work on it. I could not get the CATIA license. So the figures today are going to show primarily NX, and in this case, NX 6 is what I have on my my laptop or what I was running. And so this illustrates that you go to the File menu, go down under Import, and you will notice that you can either bring in an STL type file or you can bring in an IGES file. In CATIA, it's a similar thing. You basically go to the File menu and open a file, and as you bring up the Open dialog box, you have to change what type of file you're looking for, and it will import either an STL or a IGES file, very similar to what you see on the screen. So we find the either STL or the IGES, whichever one you save out of HyperMesh. You find that file and you bring it into your CAD system, and it should look something like this image when you bring it in. The thing that you should realize is that you have no model parameters. So if you look at your history tree, either in NX or in CATIA, you'll notice that you have no model parameters. You'll notice that you really have no features or feature structure. If you look at the little image on the right, you'll see all of these body things, body 0, body 1, body 2, body 3, and so on. You'll also find that the file, if it was originally, you had your design space model, if you had that originally linked to the skeletal model, there is no skeletal information that was brought back from HyperMesh into this file. And so really it ends up being a fairly unusable file. If you kind of turn on different visualization, if you turn on edges and things like that, you will be able to see all of the kind of mesh data. And then what I've done here in this example is you'll notice on the tree area that some of the boxes, some of the body objects are turned off, and others are left on. So I have a half a dozen parts or objects that I've left visualized, and the other ones I've unselected. The reason that I did that was to try and illustrate to you that there's no rationale as to how these body things are numbered. You'll notice that body 3, 4, 5, 6, and so on are all turned on. Some of those happen to be close to each other, but others are a long ways away, and so there's really no logic to how these triangles are numbered or collected, which also makes this file fairly difficult to work with. So that's one of the problems that you'll see in trying to use this data or work with this data, is it's very random in its order. From our last lecture, we talked about this notion of smooth faceted surfaces. And this is an example that Shane Larson had in his research. And if you remember, we identified some actual problems that he discovered. And those problems were duplicates. And so that control arm model that you bring in, you will find out that there's duplicate surfaces that are kind of representing the same basic space. So in this case, we have a green and a blue triangle that represent the exact same space of the orange triangle that's sitting below that. And so that was a problem that we talked about last time. Another problem that we talked about is this notion of quadrilaterals, which means you'll have a triangle that represents a space, but you may also have below that, you may have a rectangle that represents not only that space, but some other space that needed to be covered by this quadrilateral. And then we talked about non-manifold, where objects, the way they are kind of linked up and connected up, they have singularity and cross at a single node, which makes it impossible to try and sew all of these spaces together into a single solid. So these surfaces or planar faces come in as disconnected surfaces. If you tried to connect them all up so that you could join them together and then transform this into a solid, you would find that there are these non-manifold spots that would not allow it to join or not allow it to be transformed into a solid. So with all of those problems, are there yet still other problems that you're going to potentially run into? And this is a little video that I hope plays fairly well, but it shows another problem that you may encounter. And so I'm hoping that you can see this. We're zooming in on just a little area of this control arm, and then we're selecting things, and so there's little facets there, but I don't know whether you can appreciate what's going on. Can the students here appreciate what we're chirping across? So if you look real carefully, there's a triangle that's totally missing. There's a hole that exists kind of back in there. And so that's another, it's not just a problem of things crossing strangely. You may have a small little triangle or a sliver face that just isn't closed up. And so that's another problem with trying to convert this thing to a usable solid to make sense of it. And so the question really is, well, then how do I work? How does one, how does an individual even work with this to make any kind of sense out of it? So here is my recommended approach to trying to work with this very ugly, faceted model. The first thing that you should do is you should definitely use a layering convention to organize your model. If you have kind of forgotten, the BYU students, if you've forgotten how to do layering, the TAs can help you with that. That's a technique that we teach in 172. For the remote students, a layering approach is something where you can put solids on a group of layers, you can put surfaces on another group of layers, you can put sketches on yet other layers, and layers are nothing more than kind of, you can think of it like transparencies that are three-dimensional. When you put objects on a layer, you can hide that layer or turn that layer off, and the entire three-dimensional object that was on that set of layers will disappear. So layering is important. You need to think about importing your topology file into your skeleton file that controls that particular object, or import it into your design space model, your original kind of roughed out shape, import it into that file so that you can get an appreciation as to what area has been removed. You want to, if you bring it into the design space model, you want to just use what you set up as non-design space. You want to just accept that information as it was represented in the original file. If you just bring it into the skeleton file,